particular nonlinear wave equation called the nonlinear Schrodinger equation. So nonlinear wave equations do not satisfy the superposition principle. So one interesting phenomenon to study is the interaction of coherent waves, each of which is individually well understood what happens when they interact. It's certainly non-trivial in the nonlinear case. And the other major new phenomena you get when passing from linear to nonlinear is singularity formation. So we're focusing on singularity formation, which we call blow-up in this subject. So this is the equation. U is complex valued. I put the plus here. That's called the focusing case. There was this sigma sub c, which is d over 2 minus 2 over p minus 1, which is that the norm, so that the h sigma c dot norm is scale invariant. And sigma sub c is equal to 0 when p is equal to 1 plus 4 over d. And that's called the L2 critical, or for us, just critical case. And that happens when d is equal to 2 and p is equal to 3. And that's the nonlinear optics, the setting, the physical setting in nonlinear optics. But also p equals 5 and d is equal to 1 is also, p equals 5 is nice because then it's u to the 4u. So that's a nice algebraic power. So last time I mentioned the properties of the ground state. So we have this Q. Q there is a smooth, well, at least C2, exponentially decaying solution to this, which we call the ground state. It is the solution of minimal mass among all such solutions. And this is the ground state. And we recall that you first come across this equation investigating solutions by the desire to locate a stationary solution, stationary coherent solution to this equation. And this is called a solitary wave. All right, but the ground state satisfies a number of variational properties, which leads to the following. So we showed that if, or at least we stated, so last time we showed that if, so we're restricting to, I think mostly today I'll just restrict to p equals 1 plus 4 over d, so that assumption is always in place. So if we have initial data whose L2 norm exceeds or matches Q, then blow-up is possible. If the L2 norm is less than Q, then blow-up is not possible. That follows from the sharp Gagliardo-Nuremberg inequality and the conservation of energy. And if you go a little bit above in mass, so you're in a delta window around the ground state, then this variational characterization of the ground state kicks in, and you can say that if this is true and blow-up occurs, so if this is true and u of t blows up at some t star positive, and remember that that means that the gradient of u of t in L2 goes to infinity as t goes to t star, it has to. Otherwise, well-posedness theory would allow us to continue the solution past t star. Then there exists parameters whose behavior we don't know, but we just know that there are parameters, gamma and x of t are d, such that lambda of t to the d over 2, u of lambda of t x minus x of t, here, t minus e to the I gamma of t q of x minus x of t in h1 is less than epsilon. So for each epsilon there exists a delta such that this holds, and lambda is taken to be a normalized version of the reciprocal of the L2 normative gradient. Like that. Yeah. Okay. So it tells us that as we blow up, the solution is modeled by a adjusted version of Q. And you put the scaling on this side, so that you get epsilon on that side. So you're working with H1. So if you want to put lambda into the Q, which actually I prefer that, it looks a little more natural, then the epsilon has to change to lambda to the minus 1. So this lambda, this is going down to 0 as t goes up to t star. So just look at what's happening at the level of the gradient. So if you scale in the equation here, you have to say that u of x t minus e to the I gamma of t lambda to the minus, so it's lambda of t to the minus d over 2 q lambda of t to the minus 1 of x, write it like x minus x of t over lambda of t, right, so it's the gradient of that whole thing in L2. It's not less than epsilon, but it's less than epsilon times lambda to the minus 1 of t. So yeah, so let me. Okay, so lambda is going to 0, so that's actually diverging. Where's my? Yeah. Prefer to write it like this. Okay. So you have now a right-hand side which is diverging. However, the size of this is of size order 1 over lambda. Whereas the right-hand side is epsilon over lambda. So this is actually saying something, right? The leading order behavior of this is given by this expression. And then in L2, you would get, if you wanted to write the L2 comparison, then you would have the L2 norm of the difference bounded by epsilon, not epsilon over lambda. So this is a little more natural in that we put all the parameters over here. But we have to remember that the comparison is one that leaves us with an error, which is still diverging. Okay. So fortunately, we can simplify things by restricting to, say, 2 dimensions, radial solutions in 2 dimensions, and then the x of t can be taken to be 0. So that just leaves us with 2 parameters, gamma of t. So in the radial case, you can argue that the blow-up would have to occur at the origin. Otherwise, you would have too much mass distributed around a sphere. So we can make a simplification to the case when x of t is equal to 0, but we still have 2 parameters, gamma and lambda, to understand. And this theorem tells us nothing about what they're doing. Now, when u0 is equal to q in L2 norm, there's a special solution. So via the pseudo-conformal transform applied to the ground state, e to the itq, you get an example which is this, e to the I over t star minus t, e to the minus I x squared over 4 t star minus t, 1 over t star minus t to the d over 2, q x over t star minus t. And that becomes singular at t star. You see that the q is then contracted to a point as we approach t star. So this statement should be true in this particular, so an exact, this is an equal sign, it's not an approximate, it's an exact solution. The statement should be true. So what is the gamma and the lambda? In this formulation, there's no quadratic phase. However, if you look at what's happening, the x is really x over t star minus t. So you have x over t star minus t squared times t star minus t. So like if you were to Taylor expand this exponential and look at it, the q is exponentially decaying. So you have e to the minus I x squared over 4t star minus t is equal to 1 minus this plus dot, right? And then when that's multiplied by a q at x over t star minus t, then multiply it here. So q has this nice exponential decay, so you think of it as effectively compactly supported. So this is living in a t star minus t neighborhood of the origin. And then in that neighborhood, this term is small. And so this expansion, the dominant term is 1. So effectively, this is a lower order contribution in this expression, even though the way it's written, it's diverging. So that can be erased, and then you take gamma of t equals 1 over t star minus t, and you take lambda to be t star minus t. And so theorem works. Okay. Now it turns out that's what happens. That's what must happen, in fact, if the L2 norm of the solution is exactly equal to Q. That's a theorem of Merle that I mentioned but didn't prove. It included a simplified proof by Hamidi and Karani in the notes. So that's what must happen at that point. But as you move into this vicinity where you're strictly between these two, then that type of blow-up is still possible. In fact, it was shown by Bourgain and Wang that there are solutions that blow up like that. But it's relatively rare. What's the generic behavior, in the sense that it's stable, it represents an open set, is negative energy solutions for which, so the stable behavior in the range has lambda of t not equal to the power 1, but instead the power a half, corrected. So it goes to 0 a little faster. That's the best way to write it. Okay, so if that weren't here, then this rate would be the lowest possible. There's the well-posedness theory enables us to prove a lower bound on the blow-up rate, and that would be it in this case, power 1/2. But what actually happens, and this is not easy to see why this happens, but what happens is that this goes to 0 a little faster. So that's, if you take t minus t to the minus 1, so that's going to infinity, the log of that going to infinity, the log of that going to infinity, and that's in the denominator, so that makes this go to 0 a little bit faster. But it's, of course, this log goes to infinity extremely slowly. It's so slowly that you wouldn't see it numerically. What they see numerically is that the rate is not exactly power 1/2, but they don't see actually log, because you just give it a moment's thought. If t star minus t is like 10 to the minus 100, then a log of that, 100, log of that, 10, so. So a numerical resolution is certainly going to break down by time like 10 to the minus 16 or so. All right, so that's called the log-log law, and it took the numericists and the physicists a long time to figure out that that's what was happening. So we will discuss that. Now, okay. And you can explain what's happening to gamma, too. I have a precise formula for that. But when you get to this subject, where you want to understand the behavior of the parameters, the so-called precise dynamics of blow-up, then you have to understand the Hamiltonian structure of the equation involved. So what we're doing is we're looking at a solution which u of t, which we think of as floating around in some phase space, which happens to be a function space L2. And then there is here a two-dimensional submanifold of the phase space, which is spanned by e to the I gamma cube, 1 over lambda to the d over 2 q of lambda x. So we have a submanifold. We call this a solitary wave manifold or a profile manifold. Which is I'll call it u sub gamma lambda, where gamma lambda are the parameters. So this is a 2D, two-dimensional submanifold. of the infinite dimensional phase space for the Hamiltonian dynamics, which is L2 of Rd. So we'll spend some time discussing this, but so then U gamma lambda of x is e to the I gamma times 1 over lambda to the d over 2 q of x over lambda. And I've taken x of t, the shift, to be 0, so I assume that take u to be radial. But you don't have to. You can actually prove these results in the non-radial case too, but certainly make any simplification you can initially. All right. So this, as we vary gamma, as we vary lambda, we span a two-dimensional submanifold of this infinite dimensional phase space. And we know by this result that the solution u of t is hovering close to that submanifold. So to understand the dynamics, it's natural to take wherever you are off of this manifold and project onto it. And then as the u of t varies, you follow the projected path on the profile manifold. So what kind of projection are we talking about? It's a symplectic projection because it's a Hamiltonian system. Okay, so we want to symplectically project, and I will define the symplectic form in detail in a moment, but I'm giving you the full preview right now. So we look to symplectically project. U of t onto the profile manifold. Now the problem with that is that it turns out that this profile manifold, as it's written, is not a symplectic submanifold in the sense that it's degenerate. So you have to, in fact, augment the dimension and consider a four-dimensional manifold. And that's why I think this is why it was so hard to figure out what was going on. So what you have here are two tangent directions. At the reference point on this manifold, the standard reference point would be take gamma comma lambda equal to 0 comma 1. Standard reference point on that manifold. What are the tangent directions? Well, you have two of them given by differentiation with respect to lambda and gamma. And yeah.
What is interesting to look like UT, like this projection?
Yes.
To be like a basis or some, from some sense. And
Yeah.
try to understand UT like expansion complete with respect to this manifold, profile manifold.
Yeah. The idea to consider this profile manifold comes from the theorem that we have. That we know that this flow is going to hover close to it. And then we'll, by looking at it, doing a spectral analysis of Q, which I discussed later, it's suggested that we have to augment it to is actually a two-dimensional slice of a four-dimensional piece. And only by projecting onto the four-dimensional thing do you actually understand what's going on. Because this is degenerate, it's just a... but it has the two dimensions, so there's two directions. The way we understand this is that there's two directions. At this base point of reference, if you just take the derivative and then you set derivative with respect to gamma, you get an I, you set gamma equal to 0 and lambda equal to 1, you get IQ. If you take the derivative with respect to lambda, then you get what we usually write as capital lambda Q, where that is the operator that gives you d over 2 Q plus of x plus x dot gradient of q of x. So I have to differentiate with respect to lambda. There's a lambda on the outside and lambda on the inside, so you get two terms. Yeah, but right, so it's minus, okay. Yeah, so there's two directions, two tangent directions we've identified, but we're missing, turns out we're missing two others. And just to give you the answer long before we'll actually get there, what you have to do is consider, so we call this M. The manifold is M. Then M really should be extended to a U, which depends upon gamma B, beta lambda, where U gamma B beta lambda of x is e to the I gamma 1 over lambda d over 2 z b beta of 1 over lambda x, and z which depends upon b and beta, solves an equation, which is p minus 1 is 4 over d, like the ground state equation, but there's extra terms. And the idea to extend it in this direction, so it comes from a spectral analysis of Q. Okay. All right, so there's two extra directions that we add, and B and beta are small, but they're non-negligible, especially B. And the sigma is something that you find that you have to add. It vanishes to infinite order exponentially as B beta goes to 0. So in fact, you can transform and convert B and beta into one or the other. So you just take beta equal to 0 and study this for B. Then the expression for sigma is like e to the minus pi over b, so it vanishes exponentially fast. But you have to add it, in fact, to make this thing have finite energy. And that's what made the problem so hard, I think. So yeah, so you extend it this way, and what that does is you can differentiate this equation with respect to b or beta and figure out what adding these extra directions does for you. But it gives you so if you do dB of u at now the new base point of reference is 0, 0, 0, 1, then we get minus a half I y squared. Yeah, so I switched, right. Okay, so that, or and d beta u. And it's actually okay. Oh, yeah, rho. L plus invert. Okay, so well, it's something I have to define that later on. So okay, that's a certain operator, and this is in the orthogonal to the kernel. You can get that. So these directions are, and certainly not a priori obvious, why we have to extend it like this. So we have to start from scratch, explain what we mean by NLS is a Hamiltonian system, explain how the linearization of around Q comes into place and how to derive its spectral properties. Okay, but once you've extended it like that, you get something that's non-degenerate, the so-called symplectic submanifold. You can then project, and the projected dynamics will be how the parameters evolve. And then arguments involving conserved quantities for the NLS flow can be used to build a Lyapunov functional, which helps you prove that the flow is actually trapped close to the manifold. So it's a Lyapunov functional. The ideal Lyapunov functional will be one that would vanish on the profile manifold, but grow quadratically as you move away from it. And then if you knew that the Lyapunov functional were conserved by the flow, that quadratic growth would trap you close to the profile manifold. Okay. So now we can start with so NLS has a Hamiltonian system. So we need a phase space, and we'll call that N, because the profile manifold I use M, so I'll use N for the ambient space, and that's infinite dimensional function space, L2. So this is our phase space. And then you're supposed to look at a symplectic form. So symplectic form is a two form. You have to plug in tangent vectors. So you regard L2 as a manifold. It's a linear space. You just regard it as an infinite dimensional Hilbert manifold. And then if you look at the tangent space at a particular point, any direction at a particular point in a linear space is just identified with the space. Since N is a linear space. So if you're at U and you want to consider directions away from U, it's the same thing as considering elements of N itself, just translated with the base at U. So then when you speak of a metric, so our symplectic form comes from a metric, which is often the case with these Hamiltonian systems. So the metric, you have to plug in two tangent vectors, but tangent vectors are just elements of L2, so we have V1, V2. The metric at a point U is actually independent of U, and it's just equal to the real part of V1, V2 bar. So this is a real inner product. So whenever I use the brackets, I actually mean this inner product. I don't mean the integral of V1 against U bar. I mean the real part of that. All right, and then if you have a metric and you have an operator J, which maps tangent space, which maps the tangent space at U. So really J would, in general, depend upon the base point, maps the tangent space to itself. In our case, it's all independent of the base point. Element of the tangent space is just an element of L2. All it does is it sends V to minus I V. Then that operator J, coupled with the metric, gives you a symplectic form. Omega at U of V1, V2 is the metric V1 J inverse V2 at U. And then again, everything is independent of U, so in our particular case. So it's just throwing an I in here, and then taking the real part, so it's actually the imaginary part of the imaginary part of V1 V2 bar. So that's a non-degenerate 2 form on this space, and that's what a symplectic form is. Okay, so then once you have a symplectic manifold, you introduce a function on it, a Hamiltonian, and consider the corresponding Hamilton vector field. So we have introduced a Hamiltonian, which would be the energy. And then in general, so a Hamiltonian is a function from n, the manifold, to the reals. That's certainly a nonlinear function. And then once you have a Hamiltonian, you can get a Hamilton vector field. This is given by the general prescription that it should be the interior product. So it's you should have omega at u of v x sub h at u equal to dh at u of v for all v in TUN. This is just a way of writing the interior product in the direction of x. So x sub h is then a mapping that accepts u. So it goes from n to the tangent space of n. In particular, it takes x sub h at u and gives you something in the tangent space at u. That is a vector field, and it's called the corresponding Hamilton vector field. So the vector field associated to h. All right, but in our case, the symplectic form is associated to a metric. So fortunately, yes? Yeah. Yeah. Yeah, right. So I like to regard it as L2 because so then the Hamiltonian becomes densely defined. So it's just like an analogy with linear operator theory where you consider a Schrodinger operator as densely defined mapping L2 to L2. Sorry. Yeah, I'm sorry, I should have mentioned that. Yeah, because if you make it H1, then you have to regard the like the cotangent space as H minus 1, and it just doesn't seem to work. Yeah, so once you have a metric, then you get an identification between tangent and cotangent bundles as to the raising and lowering. Right? So you take one form and you raise it, and you get what we call the gradient. So in geometric language, that's a dh at u of v is equal to the gradient at u h paired with v, the metric. So we take that and put it back in over here. So if I pass from the one form dh to it's the gradient, then I have v gradient h at u. But in our case, we define the symplectic form in terms of the gradient too. So this is v j inverse x h at u. And so this is supposed to be true for all v. So we should have j inverse x equal to the gradient. So conclusion is that x Hamilton vector field is j times the gradient.
So
Yes.
we could have gradient of u and 2.
Yep,
For instance, if you take the Hamiltonian,
yep,
defining standard could be plus infinity. Usually you take the Hamiltonian, define it in standard
okay, I'm sorry. I didn't follow, I'm sorry.
That's the
Yeah.
rest of u,
Right,
because this gradient of u could not have sense since the n just n2.
yeah, well, it has sense on a dense submanifold.
Would be plus infinity.
Yeah, right, so you have to restrict to a dense submanifold. That's right. But you still regard that dense submanifold as belonging to L2, so that when you flip between tangent vectors and cotangent vectors, it's L2 to L2, not H1 to H minus 1. Yeah, I think it's all point of view, and it effectively really only uses this in a formal sense anyway, so so I can always just say, well, right. So then what is, so then the corresponding flow, so when you have a vector field, you can look at the flow. So d2u equals j gradient of h. That's the way people often write a Hamiltonian system. So what is the gradient in our case? So if you have this h like this, what is the gradient? So in fact, we need first and second derivatives. We're going to consider linearization, so I might as well discuss that. So when you have a function on a vector space, then you can Taylor expand. And initially, this is just like in calculus of several variables. The first derivative is then a function. So it's epsilon squared. So the first derivative is when evaluated at a point u, is a linear map from the vector space to the reals. So it's just a functional. The second derivative is a bilinear map from n into r and so forth. And then with this inner product, what you can do is write this as h of u plus epsilon, and the h prime being a linear map, just by the Riesz representation theorem, you just view it as a function itself, an element of n, paired with v. And the bilinear map can be associated to a self-adjoint operator, 1/2 epsilon squared, h double prime of u, v, v. So using the same notation for h double prime of u is now regarded as an operator from n to n. So let me finish writing this over here. So h prime of u is now just an element of n, and h double prime of u is a linear map from n to n, which is self-adjoint with respect to, because the second derivative as a bilinear map is symmetric, so it's a self-adjoint operator, self-adjoint with respect to this inner product, v1, v2, which recall is the real part of v1, v2 bar. So Right. So those are the standard identifications. So when you compute it in the case of this Hamiltonian, you just plug in, you take u, you replace u by u plus epsilon v, and you expand it out, and then use this procedure for computing, reading off what we mean by h prime of u and h double prime of u. So what we get is h prime of u is minus Laplacian u minus u to the p minus 1 u. And that just comes because you have the epsilon term in the expansion of gradient u plus epsilon v is a gradient of u paired with gradient of v. You integrate by parts, a gradient off of v onto the u, and you get the Laplacian. And h double prime of u is more tedious to compute, but it's the operator minus Laplacian minus p plus 1 over 2 u to the p minus 1, so it's multiplication by this, the operator multiplication by that, minus p minus 1 over 2 u to the p minus 3 times u squared times c, where c is the operator of complex conjugation. The operator of complex conjugation is actually self-adjoint with respect to this inner product. Okay. Right. All right. So I'll come back to. I will need the second derivative in a moment, but to connect to what I was just talking about, we just need h prime. H prime of u is the gradient of u in the geometrical sense. And so when we say Hamilton flow is dtu equals j h prime of u, and j is minus I, and h prime is minus Laplacian minus u to the p minus 1 u, you get NLS at last. So here is that issue that you were mentioning, that the h prime of u is not really an element of L2. It's an element of h. Well, it would require that u belong to H2. Okay. All right. So while we're at it, mention that H is not the only Hamiltonian that's involved in the analysis of NLS, because there's conserved quantities. So there's other Hamiltonians. So you can take M, not the profile manifold, I'm using M for mass, 1/2 u L2 squared, P, the momentum, and something I denote V for virial functional. Okay, when you compute M prime of u, you get u. Compute P prime of u, then because of the imaginary, and you have to relate this to an inner product which is real part of something, and I shows up. So you get I minus I. Yeah, minus I, gradient of u. And V prime ends up being minus I lambda. So then when you multiply by j, you get Hamilton vector fields, and that's minus IU, and j p prime of u is minus I times that, so I get minus the gradient of u, and j v prime of u is minus lambda u. So we've seen these before as differentiating with respect to certain parameters, differentiating with respect to phase, with respect to translation, and with respect to scale. So what you have is Nether's theorem. So if you define the Poisson bracket between two Hamiltonians, say H and M, then by definition, that is, you take the symplectic form, you evaluate at Hamilton vector field associated to H and Hamilton vector field associated to M. So that's just the definition of this. But when you put that in terms of the metric, the omega is, so the xh is jh prime at u, and the omega says put j inverse, and then the xm is jm prime of u. So you have a j inverse j, and so it's just an m prime. So it's called the Poisson bracket. And then Nether's theorem says that if, well, this version of it at least, there's also Lagrangian versions. Says that if two functions Poisson bracket equals 0, then m is conserved by the h flow, and also you actually get that h is conserved by that. It's a symmetric statement, m flow. So if you take h and m as I've defined it, this statement, the mass is conserved by the NLS, right? That's, we already know that by direct computation, but here you derive it by saying if I take u to evolve according to h, I have dt of m of u is equal to m prime at u paired with dtu. Right, by the chain rule. And dtu is evolving according to h. So dtu is jh prime, and that is exactly what we wrote as h, Poisson bracket of h and m, evaluated at u. So I should have made that clear that Poisson bracket gives you a new function, accepts u and returns a number. And so if that's equal to 0, then, right. So you have here several commuting flows. Well, actually, so with the v, Poisson bracket is not 0, but it's somehow nice. It's, if you recall, well, no, actually, I didn't write it. What I wrote was a virial identity in the form of the second derivative of the variance gives you 16 times the energy. But actually, an intermediate version of that is that the time derivative of this is 16 times the energy. And so what that is saying is that the Poisson bracket of v and h is the energy. So it's not 0. But it is sort of, it is preserved, and so it is structurally significant. Okay, so that's a little bit of a side note. We will use these other functionals in the analysis of dynamics. Okay. Didn't want to lose track of time. Yeah, so actually it's a good time to take a break. So when we come back, I'll use these functionals, and it will help us to study the linearization of NLS.